In this video, we're going to be looking at domain and range, and we're going to look at how to examine domain and range both graphically and with an equation. So you can see here at the top of the screen, I just have the quick definitions. Domain, the set of all allowed x values or inputs for a function or relation, and range is the resulting set of y values. Key thing to remember is that domain is x, range is y. Very important. That'll help us keep things straight. So first we're going to look at that graphically. So I have my first little graph here. I found this online. I think this is a nice visual representation here. So remember, domain is x values, range is y values. And we want to list in this example the domain of this navy curve here that we have. So domain, that means we're looking at x values, and we're going to be always putting domain and range in interval notation. So basically they highlighted across the top here for us what we need to write. The x values of our function start at -3. Notice that's an open circle, so we'll use a parentheses here. And x values, the graph curves down and curves back up, but the x values continue all the way over here until x equals 1. And notice that one is a closed circle, so that will be a square bracket. That would be the domain of this graph. The range, on the other hand, we're going to look at the y values, so we're going to be looking at the vertical axes. Again, they highlighted it for us over here on the side in green, but we can see that if we're just looking up and down, this graph starts at -4. That's the smallest value that it covers. That's a square bracket because of the closed circle. And this graph goes up to a y value of 0. Now they do have an open circle here, but I think 0 is included in the graph because even though there's an open circle here at x equals -3, the graph does touch the point 0, 0 right here. So I would put a bracket there for our range. So those are the domain and range. Okay, so when they have these nice little orange and green lines on the side, it's relatively easy to see, but we want to look at some graphs where we only have the graph and nothing else. So here's our first example. This is just a linear relationship here, a linear function. So what would the domain be and what would the range be? Okay, remember domain is x values, so we're looking horizontally. We can see this graph continues to the left and it continues to the right, on and on forever. So whenever we have that case, the domain is all real numbers. And in interval notation, that would be the interval from -infinity to +infinity. Similarly on the range, if we're looking now at the vertical change, the vertical axis, it keeps going up and it keeps going down. So again, -infinity to +infinity. Okay, our next example looks a little different. We don't have just a linear function here. This happens to be a quadratic. So let's think about domain and range here. Again, domain would be the x values, so we're looking in this direction. Okay, and we can see that although this is slanted up, it also is going out, and it keeps going and going both to the left and to the right. So the domain is still, just like the last one, all real numbers. For range, we want to look at the vertical axis, and we can see it keeps going up and up forever, but it does not keep going down and down. It's got an ending point right here. The range actually ends at 0, starts at 0, smallest number, starts at 0 and keeps going up to +infinity. So the domain is all real numbers here, but the range is only from 0 and on up from there. Here's another example. This one is not actually a function, but it's a relation. We can still talk about domain and range. Domain, again, x values, so we're looking side to side here. And you can see that it keeps going to the right, but it doesn't keep going to the left. So this time, our domain is 0 to +infinity. Range, we're looking up and down. And again, kind of like our parabola, this keeps going up and keeps going down forever and ever. So our range is all real numbers. And here's our last graphical example. Domain, remember domain is x values, so we're looking side to side. Where does the graph start and where does it stop? And it starts right here at x equals -2 with a closed circle, so we will have a square bracket, and it continues. The rightmost value is right here at x equals 1. So there's our domain. For range, again, we want to look up and down, and it looks like the lowest value on our graph, our smallest y value, is 0, and our largest y value would be 3. Again, closed circles there, so we have brackets on both of our sets of numbers. Okay, we can also look at domain from an equation. We're not usually going to be looking at range from an equation. That's a little bit trickier. You can do it, but we're not going to be doing that in this video. When we look at domain in an equation, the couple things to keep in mind. We never want our equation to be undefined. Undefined would happen if we tried to divide by 0, okay, so no dividing by 0 is allowed, or if we tried to take a square root of a negative number or a fourth root, any even root of a negative number. Those two are where we run into problems. So a nice basic little function like this first one, 5x plus 4, if we graphed that, that would just be a linear function, and that's going to have a domain of all real numbers, because there is no value that we could plug in here for x that would cause us any problems. We could calculate this for very large number of numbers, for x for very small numbers, 0, fractions, anything is okay. So the domain is all real numbers. Similarly here we have a polynomial, and although it's a little more complicated than that last linear example we just looked at, again, we can take any number and raise it to the 4th power, to the 3rd power, and x in there. So this one also all real numbers. And a lot of times your domain will be all real numbers. The two cases that we are going to have to watch out for the most is like this one. What if we are dividing by our variable? Okay, we already said that we cannot have a denominator equal to 0. So in this case, our domain is not all real numbers, because if we plugged a 0 in here, we would have 1 divided by 0, and that's undefined. So really, all real numbers except for 0 is what we'd like to stay for our domain. Again, we want to put that into interval notation. So all real numbers would look like this example above, -infinity to +infinity, but we have to stop along the way and kick out that 0. So the way we write that in interval notation is we start at -infinity and we stop at 0, parentheses, because we do not want to include that 0. That would give us an undefined expression, and then we start up again at 0 and continue on to +infinity. This is the interval notation for how we represent all real numbers without just kicking out one of those single values, in this case x equals 0. Okay, same idea here. Now we have an even root, and we said up above we can't have any negative values under that even root if we want to have a defined function. So in this case, x has to be greater than or equal to 0, because we can't take the square root of a negative number. So in interval notation, we would start at 0 and continue on to +infinity. There's our domain. Okay, then these two add a little bit more, not much, but same thing going on here as we saw in the example above. We can never let the denominator be equal to 0. So we want to say that 3x minus 7 cannot be 0. Add that 7 over, and divide both sides by 3. So our domain is all real numbers except for 7/3. 7/3 doesn't work because that would give us a 0 denominator. So again, writing that in interval notation, we would stop at 7/3 and exclude it using our parentheses. Okay, same idea over here. We don't just have an x under the radical, but we have an expression. Same idea though, that expression, whatever's under that radical, has to be greater than or equal to 0. Otherwise we get an undefined result. So we just have to solve this little inequality. Divide both sides by 5. We get x must be greater than or equal to 4/5. In interval notation, that would be starting at 4/5 and continuing on to +infinity. Okay, in our last two examples, I wanted to try something a little more complex. So this first one is just a single radical. So we know from what we've been talking about so far that whatever is under that radical, in this case x squared minus 4, whatever's under there has to be greater than or equal to 0. Now this is a polynomial inequality. It happens to be a quadratic inequality, but remember we have some special solving skills we need to use for an inequality like this. We want to go ahead and factor that. And then we get our two values. Remember, these are not our solutions, these are our boundary points. Okay, we plot those onto a number line. And those two boundary points break our number line up into 3 sections. I like to label these with letters just so you can help keep track of what I'm talking about here. So these two boundary points break our interval into 3 sections, and we need to test each one of those sections. Remember up here we were looking for where are the values greater than or equal to 0. So for interval A, maybe my test point might be x equals -5. -3, -4, -100, anything in that interval works. So we plug that into our inequality. I don't care what this answer really is, I only really care about the sign. So -5 minus 2, I know that's going to give me a negative number. And -5 plus 2, that's also going to give me a negative number. When I multiply a negative times a negative, that's going to give me a positive result. So that means interval A is positive. Now I need to test interval B, and I always like to use 0 when I can because that usually makes my calculations easier. So I plug in 0. This one's pretty easy to do in your head. You end up with -2 times +2, which is -4. Again, I don't care so much about the 4. I care that my answer is negative. So interval B, everything in that area is negative. And finally, interval C, maybe for my test point, I'll use x equals 4. Plug it in. 4 minus 2 is positive. 4 plus 2 is positive. A positive times a positive gives me a positive answer. Okay, so now I'm going to switch colors here so you can see what I'm doing. I'm looking back here at this inequality I had set up. And I said I was looking for areas, x values, where this is greater than or equal to 0. So that would be the positive sections on my number line, the intervals that I labeled A and C. So the domain would be the x values in those intervals. Start at -infinity, go up to -2. We do want to include -2 because 0 is okay. We can take the square root of 0, just not a negative number. Then we start up again at +2. And go to infinity. That would be the domain of our function. And then this last one puts together both the idea of having a square root and having a denominator that we have to deal with. So there's kind of two pieces we need to put together here. So let's just first look at the top of this rational equation. We can't take the square root of a negative number, so the first piece of my domain is that this 3x minus 8 has to be greater than or equal to 0. So 3x greater than or equal to 8, so I know that x has to be greater than or equal to 8/3 to take care of that radical that's on the numerator. Now the other problem here, the other piece of this puzzle, we also have a variable in our denominator. So the other issue is that x squared plus 4x minus 32, that whole denominator cannot be equal to 0. Okay, so we can factor that. X, 32 would be 8 times 4. If I make that a +8 and a -4, I get my 4x in the middle. So that means x cannot be equal to -8 because that would give me a 0 denominator. Also, x cannot be equal to +4. That would also give me a 0 denominator. So I have boxed in here the two pieces of our domain, but now I need to put these two together into one interval statement. So if I just had this one on the left, x greater than 8 or equal to 8/3, that would look like this. Okay, but that's not enough information. I also have to exclude -8 and 4. Well, think about -8 for a minute. If we drew this on a number line, what I said so far, 8/3 is about 2.6, 2.67. So I'm saying that my domain has to include these numbers right here, from 8/3 on up. Well, -8 would be way down here somewhere. It's already excluded. That's not in this shaded area, so that one's taken care of. -8 is out of my domain already. But +4 would be right about here somewhere, right in the middle of my shaded section. So what I have to do is I have to take this interval that I started with and I have to exclude that value of +4. So that's going to be the same kind of thing we did up in the previous examples. I'm going to start at 8/3. I have to stop at 4, use a parentheses to exclude that value, then start up again at 4 and go to infinity. This is the domain that combines both of the pieces of information that we found above.